Hey, everybody. Hey, we're going to finish up chapter 4, and actually, we're going to try to do a big chunk of chapter 5 also, because chapter 5 is pretty much straightforward and it follows only two concepts. This one deals with the larger set of inequalities, chapter 4, section 6. It deals with inequalities of polynomials and inequalities of rational functions. Remember, polynomials are large functions where they have many terms. And then we have rational expressions where it's made up of two functions, one on top, one on the bottom. And the only thing we have to make sure of is that the denominator does not equal 0. When we talked about inequalities earlier in the semester, we looked at something like x plus 1 is greater than 3. What we did is treat this as an equal sign. So I subtract 1 from both sides. And then we went ahead and so we have our number is 2. It's not included because there's no line underneath. It's not equal to. And x is greater than 2. So our line goes this way, all the way to infinity. Okay, that is what we used to look like because it's just on a horizontal line. Now we're going to go further because when we had quadratic equations or cubic equations or any nth order polynomial equations, let's look at polynomials first. Let's say we had our function was x squared plus 3x minus 10. And I want to know, when is this function greater than or equal to 0? So again, treat this as an equal sign. So we're looking at, first off, let's see where it's equal to 0 in this case. We're looking for either way. It's just that since it equals 0, we have to include that 0 value in our answer. So our function is x squared minus 3x minus 10. And let's go ahead and solve this one. Always has to be, like if this is equal, always has to be set equal to 0 to solve it. So if we can factor it, let's factor it. If not, then we use complete the square or quadratic formula. So x times x gives me x squared. The second sign's a minus, so that means they're opposite signs. The bigger number gets the negative. So what times what is 10? When you subtract them, you get 3. Now 5 times 2 is 10. 5 minus 2 is 3. So the negative, the 5 gets that, and 2 there. Set both of those equal to 0 and solve. And it's the same stuff we've been doing all along, like treating it equal to 0. But these numbers, they are our x-intercepts or our zeros, because if we plug these numbers and say equals 0, if we plug these back in the original equation, it'll equal 0 because they're the x-intercepts. So our graph will look like this. X is negative 2, and x is 5. 1, 2, 3, 4. They're solid dots because I can include. If this line wasn't underneath it, then I have open circles there. Okay, these are now called our critical values. The reason they're called critical is because, once we set it equal to 0, what this looks for, if f of x is greater than 0, that means it's above the x-axis. The values are positive. If the function is less than 0, then it's below the x-axis. So this is what we're looking for. That's the reason we set it equal to 0. Okay, now, since we've learned how to graph these things, we know that it's a power 2, so the degree is even, which means both ends point the same way. The end behavior is the same. It's a positive 1, so they both point up. So I know just by graphing that the graph will look like this at the endpoints. Again, now another thing we also learned is, since we factor this out, since the multiplicities are odd, that means it crosses at those points. If it was even, it would bounce off those points. It's called multiplicities. We also know that we have a y-intercept at -10. So all the way down here at -10, we have a y-intercept. So that's what our graph looks like. Since our function is greater than or equal to 0, we want to know what part of this graph, or what intervals, because we're looking for the intervals. Is it from -infinity to -2? Because that's inclusive. Is it from -2 to 5? That's between those. Or is it from 5 to positive infinity? Which of these intervals, if any, are greater than 0, are above the x-axis? Well, here it is, and here it is. So our solution is the interval from -infinity to -2, union from 5 to positive infinity. That's our solution. Okay, that's if we can graph it and how comfortable we are with that. Another way we could do this is, once we factored it out, we found our critical values, we found our intervals. So here's our critical values, which I'm going to call CVs from now on. They are at -2 and 5. So our intervals since these are our critical values, I can't use those. So to the left of that, I go from -infinity to -2, and since it's equality, it's from -2 to 5, between there, and it's from 5 on out to infinity. These are our intervals, so they're either above or below the x-axis. Now we pick some test values. Test values are numbers inside these intervals. So give me a number that's between -infinity and -2. I say -3. This is x equals -3. In this interval, between -2 and 5, I use 0. And between this one, I use 6, because it's not 5 or infinity. Once I get my test values and I have the intervals, and I know that what we're looking for is our function has to be greater than, since we're looking for our function has to be greater than or equal to 0, I only want positive answers. So I plug these numbers, these test values, inside my function. I'm going to use it in this factored form because that's what our function is, that factor it out to that. So now remember, since I want it, it has to be greater than or equal to 0, which is greater than, has to be above the x-axis. So I'm only looking for the ones that are positive. So if I plug in -3 in here, I get -3 plus 2, -3 minus 5. -3 plus 2 is -1. -3 minus 5 is -8. Negative is a positive, is 8. And that's greater than 0. So I can use that interval. Now let's look at 0. Plug it in this equation. 0 plus 2, 0 minus 5. So it's 2, -5 makes it -10. Is that greater than or equal to 0? No. So I can't use that interval. Now I use this last test value. So I have 6 plus 2, 6 minus 5. So it's 8, 6 minus 1, and that's greater than 0. So I use these two intervals, which is what I said earlier. So you could use either method you want to. But yet first, on the first example, I'll work it out for you with the step-by-steps. All right, so let's look at example 1 from our sheet here. So let's solve this first one. X squared minus 4x minus 5. X squared minus 4x minus 5. Here's the steps. Remove any parentheses. Set equal to 0. Which have to have 0 on one side. Factor solve for the x-intercepts. Remember, the x-intercepts are your critical values. Find the intervals. Choose test values in each interval. Plug the test value into the function. And find the sign of the answer. Remember, if your equation is like this, we only want positive solutions. So if they're negative, you don't count them. If your function is less than 0, we only want negative solutions. And then state the intervals that satisfy the above conditions. Okay, let's go ahead and work this out. So those are all the steps. In our example, no parentheses. It's already has equal to one side, so it's good. Now we have to factor it. So x times x gives me x squared. The second sign's a minus, so the two signs are opposite. And the bigger number will get that sign. So what two numbers multiply to give you 5, that when you subtract them, you get 4? 5 times 1 is 5, 5 minus 1 is 4. So 5 and 1. Since the 5 is bigger, it gets the negative sign. Now it says solve for the x-intercepts. In other words, take both of these, set them equal to 0, and solve. These are my x-intercepts. My critical values or x-intercepts. So I have it at -1, 1, 2, 3, 4, 5. Since it's an open circle because there's no line underneath it. It's a strictly greater than. Whereas I can't use those numbers. The intervals in this first interval, I'm going from -infinity to -1. Remember, it's open, so I can't use that. Then I look at between here. I look at -1 to 5. And then I look at from 5 to positive infinity. I look at all those numbers. These are the intervals. So, these are the intervals. I solved. I factored. I set it equal to 0. Now I've got to choose test values. Between -3 and -1, I choose -2. Between -1 and 5, I choose 0. I choose 6. Those are my test values. So now I plug these values into that equation, the factored form. Or if you want to, if you're not sure about your factor, then go back to the original. So I have x plus 1, x minus 5 is greater than 0. I only want where these values are positive. So -2 plus 1, -2 minus 5, -2 plus 1 is -1, -2 minus 5 is -7, negative is a positive, and 7 is greater than 0, so it works. Do the same thing here with these x values. So I have 0 plus 1, 0 minus 5. Is that greater than 0? So it's +1, -5 is -5, and that's not true, so I can't use that interval. 6 plus 1, 6 minus 5. 6 minus 5 is 1. So my answer consists of these two intervals. And again, if you are good at graphing, we knew that our intercepts were -1 and 5. Because our function has an even degree, both ends point the same, since the leading term was positive, I know that at both ends has to be up. And since when I factored them, my multiplicities were 1, so it crosses the x-axis, has a y-intercept of -5. So the only place this graph is greater than 0 are from -infinity to -1, and from 5 to +infinity. Again, you could do it either way you want to. All right, let's look at the next example. We have x squared plus 3x minus 5 is less than equal to x plus 3. And here it's a quadratic equation, and it's positive, so we want everything on this side. Whenever it's polynomial, has to be set equal to 0. So I subtract x from both sides, and I subtract 3 from both sides. So that gives me x squared. 3 minus 1 is 2. -5, -3 is -8. These cancel, so it's 0. No parentheses, has set equal to 0. Now factor it. X and x, opposite signs, bigger numbers positive. What two numbers multiplied to give you 8? When you subtract them, you get 2. 4 times 2 is 8, 4 minus 2. And the bigger number. Set them equal to 0. I need to find my x-intercepts, my critical values. Because it's a less than equal to, I can include that number. Again, since it's a quadratic equation, both ends, I know the graph is going to look like this. And it has a y-intercept at -8. -8, not -6. So I'm only looking for here, this function is less than 0. So I'm only looking for anything below the x-axis. So I know my answer is going to be in this interval. Because in this interval and this interval, the graph is above the x-axis. So I know my answer is going to be but yeah, let's go look at the way they may want you to find me the test values. Between -3 and -4, I use -5. Between -4 and 2, if you can use 0, it's always the easiest. And then from 2 to infinity, I use 3. I plug them into this equation, and I want it to be less. I only want negative answers. So this one is -5. So I have -5 plus 4, -5 minus 2. So that's -1 times -7. Negative is a positive, and that's not greater than or less than 0. So I can't use that interval, which we knew that because it's above the x-axis. 0 plus 4, 0 minus 2. So it's 4 times -2 is -8, and that's good. So 3 plus 4, 3 minus 2. So it's 7, +1. Is 7 less than 0? No. So again, it's this interval. You can use whatever method you want. All right, let's look at example 3. X cubed minus x greater than 0. Again, from our graphing phase, we know the degree is odd. So that means the end behavior goes opposite directions, either down here, up there, or other way. Since their leading coefficient is positive, we know that the right-hand side goes up. It's a positive increasing function. So the graph's going to look like this. So let's factor this out. They both have an x in common. Whenever you factor something, they both have an x, so I take it out. To see what goes inside here, I divide both of these by x. So if there are 3 x's on top, I took away 1, I only have 2 left. X divided by x is 1. Okay, this is a quadratic, so it has 2 answers. So let's set each of these equal to 0. So we have x equals 0 as one of our intercepts, our points. X equals 1 square root. So x equals plus or minus the square root of 1 is 1. So at -1, at 0, and at +1. Because this one here is x equals 1 and -1. Since we know the end behavior, and from this point it goes down, from this point it goes up. The multiplicities are 1, so they cross at all of these. So our graph looks something like this. Let's look at my intervals. I have the first interval here, which is from -infinity to -1, from -1 to 0. Now, because there's no line underneath it, I don't have brackets around the intercepts. If there was a line underneath it, then at each one of these 3 points, I would use a bracket. Then from 0 to +1, and then from +1 to infinity. Remember, I only want where the x's become positive. So I only want above the x-axis, here and here. So I know that this one and this one are going to be the only two intervals that work, because from negative infinity to negative 1, it's below the x-axis. It's negative. So I know that's not going to work. Again, if you don't know how to draw it, then once you find the x-intercepts and you find these intervals, let's find the test values. So between negative infinity and negative 1, I pick negative 2. Between negative 1 and 0, negative 1/2, positive 1/2. And I'm testing it in this. I only want to see which ones have a positive answer. So negative 2 squared minus 1. Is that positive? So negative 2 squared is 4 minus 1. This is negative 6, and that's not greater than. So again, I knew that was going to fail. At negative 1/2. So at negative 1/2 squared minus 1. So this one gives negative 1/2. Negative 1/2 squared. Negative times negative is a positive. 1/2 squared is 1/4. 4/4 is minus 1. So the bottom number is 4. 1 minus 4 is negative 3. Negative is a positive, so it's 3/8. That's a positive answer. So I know this one's going to work. So it's the x is 1/2, then 1/2 squared minus 1. Is that greater than 0? So 1/2. 1/2 squared is 1/4 minus 1. 1 common denominator is 4/4. So 1/2. Since you have a common denominator, 1 minus 4 is negative 3. 2 times 4 is 8. 1 times negative 3 is negative 3. And that's negative, so it's not going to work. And then 2. 2 squared is 4 minus 1 is 3. 2 times 3 is 6, and that's greater than 0. So these two intervals are my answer, which means that from negative 1 to 0, to 0, union with 1 infinity, that's my answer. All right, so that is inequalities in polynomials. Just set it equal to 0, factor it out, find the x-intercepts, and see which intervals are either above or below the x-axis. All right, the other half of the coin here are now rational inequalities. So this is when we have two functions, one on top, one on the bottom, and we look for some inequality. Since this is a function with respect to x, top and bottom, one thing we know for sure. We know two things. One, the only way a fraction can equal 0 is if the top is equal to 0, or the numerator. In other words, we set f of x equal to 0 and solve. Second thing we know, bottom, or the denominator, can never equal 0. Remember last section, or in this chapter earlier, we call that vertical asymptotes. It's where the denominator equals 0. Vertical asymptotes is where the bottom equals 0 and solve for x. These are the vertical asymptotes. You cannot use these. You cannot use those. This one's example 5, I'm sorry. All right, so let's look at 3 examples here. 3x over x plus 6 is less than 0. Okay, again, same as last time. We have to get rid of the parentheses. We have to get everything to one side, set it equal to 0. So set equal to 0. Simplify the left side. No. Find the critical values. The critical values here are when the top is equal to 0. So I want the zeros where it crosses the x-axis. And I want where the bottom is equal to 0. I want the vertical asymptotes. Those are my critical values. So here I set 3x equal to 0. So x equals 0. That's my x-intercept, or my 0. And I set the bottom equal to 0. That's my vertical asymptote. So at 0, because there's no equal sign underneath it, so I can't use these. I just go all the way up to them. So at 0 and -6, I have my points. Find the horizontal asymptotes. Remember, that has to do with the exponents. And the exponents, the degrees of the top is n, degree of the bottom is m. So if the top is bigger than the bottom, it does not exist. If they equal each other, then the horizontal asymptote is simply their coefficients, A over B. If the top is less than the bottom, then it's the x-axis. And remember, if n is one more than the bottom, then we have an oblique asymptote. So we do long division, just division to find our equation. It'll be a slant. It'll be an equation. All right. So my intervals are here. Because the degrees of the leading terms are both 1, my horizontal asymptote is at 3 over 1. This is my horizontal asymptote. My vertical asymptote is there. Now we want to know where the graph is below the x-axis. So my intervals are from -infinity to -6, from -6 to 0, and from 0 to positive infinity. Choose my test value. And plug them back, or factor all your numerators and denominators. So factor both top and bottom. I only want I only want negative answers. So I have 3x, x plus 6 is negative. So I have to use this equation. So 3 times -7, -7 plus 6, it's -21 over -1, makes it 21. Is that less than 0? No, so I can't use that. So that means this part of the graph is up here in the positive realm. Well, it can't cross the horizontal asymptote. How about at -1? So I have 3 times -1, -1 plus 6 equals -3 over 5. And that's negative, so it's less than 0, so this is good. So these answers are negative, so now this has to be below here. So this part of the graph looks something like this. And when x is 1, so we have 3 times 1, 1 plus 6, 3 over 7. That's positive. So, and it can't cross the horizontal, so this part of the graph looks like this. So this is the only part of the graph we can use. All right, let's look at the next example. Example 6. X plus 1, 2x minus 4 is less than equal to 1. Remember our steps. That equals 0. So we have to move this 1. We have x plus 1 over 2x minus 4. So I subtract 1 from both sides. This is 1 over, it has to be, since we have a fraction here, so we're subtracting a fraction. simplify, you have to combine fractions. You have to find the least common denominator. Since the only denominator we have is 2x minus 4, so we multiply this one by 2x minus 4 over 2x minus 4. Times 1 is 2x minus 4. Since we have a common denominator, never, even if you have multiple denominators, never multiply them, even factor that, because that'll help make it easier to find our critical values. So on top we have x plus 1 minus 2x minus 4. Now, do I need a parenthesis in this first one? No, so I can just drop the parenthesis there. But the second one has a minus in front of it, so I have to distribute. Negative times positive is negative 2x. Negative times negative is a positive 4. Combine like terms. So x minus 2x is minus 1x. 1 plus 4 is 5. So at this point, I could take the top number, negative x plus 5, set it equal to 0. So move the x over. So x equals 5. That's my x-intercept, my 0. And on the bottom, I have 2x minus 4, set it equal to 0. 2x, move the 4 over, divide by 2. So x equals 2. This is my vertical asymptote, the line I can't cross. Two, three, four, five, 6. So we have, okay, since these are equal, I can equal 0. 1, 2, 3, 4, 5. So I put a solid dot there. This is the bottom number, so vertical asymptote. So I can never use that. So I'm going to have a vertical asymptote here. And that's an x-intercept there. Since the degrees of the leading terms are both 1, I just take the coefficients. My horizontal asymptote is negative 1/2. So my horizontal asymptote goes through here. So let's look at my intervals. I'm going from negative infinity to 2, from 2 to 5, and then from 5 to positive infinity. These are my intervals I'm looking at. My test value I'm going to use here, I'm going to use 0. If you can use 0, always use 0. I'm going to use 3 here. I'm going to use 6 there. Remember, I only want numbers that are negative. That's below the x-axis. I only want answers that are below this line here. And we're going to use this equation. So at 0, so we have 0 plus 5 is 5. 0 minus 4 is minus 4. That's less than 0. What this says is this is also where my negative 1/4, that's my y-intercept. When you set x equals 0, that's your y-intercept. here's my horizontal asymptote. So from here, I'm going down like this. What happens in this middle interval when x is 3? So we have -3 plus 5. There's -1 times 3. So -1 times 3. 2 times 3 minus 4. So it's -3 plus 5 is 2. 6 minus 4 is 2. So that equals 1. So what? When x is 3, if I had colored pens, this is my x-intercept, my x-axis. This is x-axis. This is my y-axis. So when x is 0, y is -1 1/4. When x is 3, it equals 1. That means this graph is not right. Because this is my horizontal, this is my vertical. That means my graph looks like this. Not like that. And then I have another interval here. So at 3, it's 1. And it has to cross there to my horizontal asymptote. So this one fails. That means this one here is going to pass. It's going to have -6 plus 5, 2 times 6 minus 4, -1 over 12 over 8. Yeah, so this one works. So it's below the x-axis, but above the horizontal asymptote. So that's that little spot there. And this one here is everything from there. So my answer is from -infinity to 2, and then from 5 to infinity. Because it's okay all the way up to 2, because it's going like this. And here's the vertical asymptote. So this part of the graph has to go the other way, crossing at the x-intercept there. This way is above the x-axis, here's below, and here's the horizontal asymptote. So this is my answer. Sorry about that. Got myself confused over a second. All right, the last one of this check section and chapter, and then we'll move on to chapter 5. We have x minus 3, x plus 4, x plus 2, x minus 3. Let's move this whole thing over. So we have an x minus 3 minus this entire fraction. I said we did it with the 1. We just subtracted, moved it over there. Now it's a common denominator. This one has an x plus 4. This one needs an x plus 4, top and bottom. This one has an x minus 3. This one needs an x minus 3 on the bottom. So I multiply x minus 3, x minus 3. Think about it. X minus 3 over x minus 3 is 1. All I'm multiplying by 1. I'm just changing the way it looks, not the number. So I have x minus 3 minus x plus 2, x plus 4 is greater than equal to 0. And on the bottom, we have x plus 4 times x minus 3. Leave these factored. Don't multiply those. But we have to combine these because we only have one equation on top. X times x is x squared minus 3x minus 3x positive 9. That's this one. Now I do this one. X times x is x squared plus 4x plus 2x plus 8 over the bottom, which is greater than or equal to 0. I don't need the parentheses in the first one. So I can combine these two. Negative 3 is a negative 6x plus 9. Combine those. X squared plus 6x plus 8. And leave the first one alone. Now distribute that negative to everybody. So negative times positive is negative x squared. Negative times positive is negative 6x. Negative times positive is negative 8. It's still greater than or equal to 0. The x squares cancel. Negative 6x is negative 12x. 9 minus 8 is positive 1. So we simplify those. So now we've got to find our critical values. Take the top, these are zeros. Is that negative 12x plus 1, set it equal to 0. 1 equals 12x. X equals 1 over 12. So that's my x-intercept. My vertical asymptotes are at x equals negative 4 and x equals positive 3. Okay, so let me make sure my top number is correct. I didn't change numbers anywhere. That's where I messed up. This is supposed to be a 5. That number is supposed to be a 5. So this is a 5. So it needs an x minus 5 over x minus 5, x minus 5, x minus 5. So here's what, so it's going to be, this would be minus 5x plus 15. So it's going to be 15 here. That's 5. This is 15. And that's a 5. X squared is canceled, negative 12x. 15 minus 8 is 7. So this is 7 over 12. Because equal sign is my 0, I can include that point. This is 7 over 12. My vertical asymptotes are at negative 4 and 3. I cannot use these values. And my horizontal asymptote, since the top is only 1x, the bottom has 2, it's the x-axis. So this is my horizontal asymptote, the x-axis. Let's look at my intervals. We have those 4 intervals. From negative infinity to negative 4. From negative 4 to 7/12. From 7/12 to 3. And then from 3 to positive infinity. Take my test values. So negative 5. 0. So if I can use 0, I'm going to use 0. I use 1. And I'll use 4 here. Remember, we're looking for greater than 0. So we're looking only for positive answers. We only want positive answers. All right, so let me write this equation on the other side. Negative 12x plus 7. X plus 4. X minus 3. My intervals. Negative 4. 7/12. And 3. We want these intervals. Those are my intervals that I use. Negative 5, 0, 1, and 4. I only want positive answers. It's got to be greater than, yeah. So these are my intervals. From negative infinity to negative 4. From negative 4 to 7/12. Which equals, so the 0 can be included. Remember, since it equals That means the top number, whatever that 0 is, I can include, which is 7/12, which is the bracket. So at -5, we have -12 times -5 plus 7, -5 plus 4, -5 minus 3. Is that positive? Negative is a positive. That's 60 plus 7. -5 plus 4 is -1. -8. So that's 67 over 8. That works. So we can use this interval. It's above the x-axis. At this one, when x is 0, we have 7 over 4 -3. It's 7 over -12. It's not, so we can't use it. So that means this one's below. We have -12 plus 7, 1 plus 4, 1 minus 3. So it's -5, 5, -2 equals 1/2, and that's greater than 0. So I can use this. -12 times 4 plus 7. 4 plus 4, 4 minus 3. Is that positive? -48 plus 7. 8, 1. Nope, the bottom is positive, the top is negative. So it's not going to be greater than 0. So I can't use this one. Okay, we want only the graph that's above. So let's look what the graph really looks like. So we have a vertical asymptote here. We have a vertical asymptote here. And the x-axis is the horizontal asymptote. And we have an intercept at 7/12. So in this first interval, we know it's greater than 0. And it can't cross that, so we know this one's going to look like this. That's our x-intercept, and it can't cross both of those. On this side, it's negative. On this side, it's positive. So this is positive, negative, positive, and this one's negative. Since this one's negative, we know the answer is going to be down here. Because it can't cross the horizontal asymptote, and it can't cross the vertical asymptote. So that's our graph. And we only want parts that are above the x-axis. Okay, that does it for chapter 4. That does it for chapter 4. Now, let me stop this one, and then we can start chapter 5.